Thank you, Claudia, for introduction. Thank you very much for inviting me to this colloquium. Since I've been always a great respect for Erwin Schrödinger, so it is my great honor and pleasure to talk in this building, in this Schrödinger Center. And I'm going to talk about this recommender system. But before going to this talk, I'd like to say something about my history, personal history, and my background. I was grown up as a metallurgist, and my journey started in Germany, in Stuttgart. And this is Max Planck Institute for Metallforschung in Stuttgart is no more existent, but I was there in the year 1992, long time ago, 37 years ago. And before that, I used this type of high-pressure synthesis facility to sinter silicon nitride ceramics without sintering aids. This is called hot isotopic pressing instrument, and we can raise temperature up to this temperature and raise pressure up to this value. So with that, even this is nitride is typically very difficult to sinter. With this pressure, we can sinter this silicon nitride. This is a typical microstructure, and probably you know that these grains are single crystals, and these are polycrystal materials. And in between these crystals, there are grain boundaries. And 37 years ago, we investigated by transmission electron microscope the behavior and structure of this grain boundary with Professor Rure and Professor Krive in Max Planck. And since we were interested in this type of materials, we were interested in Lear materials. They are typically polycrystalline, multi-phase, and contain a lot of atomic defect. These are Lear materials. And of course, to investigate Lear materials, there has been a traditional way to investigate that, to make good quality single crystal and to do a lot of experiment on single crystal. And of course, if it works, we can put it to the physical model to estimate property of Lear materials. And there's also traditional experimental tools, which is always very useful. And if you have a good sample, then you can make some analysis, microscopy, etc., to put it in the thermodynamic laws to examine the process conditions. So all these tools are well established and quite useful. But for example, for silicon nitride, this is a problem. You cannot make good quality single crystal easily. And also, experiment is very time consuming and labor intensive. And it is limited prediction capability because experiment can be done only on pre-existing materials. So it is difficult to predict new materials. And also, because of that, it's very difficult to do inverse design. So although this is very useful, there has a lot of problems. I met first principles calculation when I was in Stuttgart in the year 1992. And this is the history of first principles calculation. And at the very beginning, it was able to compute only simple crystals like silicon or aluminum metal. But at the year 1990, they can compute some complicated crystal or defect. Though as time goes by, the precision and speed increase, but still at that time, first principles people are very much criticized by experimental people because we can handle only at the 0 temperature. They always claim that, wow, we are not interested in the zero temperature property. It is true. But from the year 2000, gradually, we were able to compute phonon to be able to compute some dynamical quantities at finite temperature. We have some contribution for the phonon calculation. And also at the same time, we were able to handle a lot of calculation, or massive calculation to put it to the database, like in NOMAD here in Berlin. And those data can be used for material science issues. So I've been working in this time. So this is the current approach to study arbitrary materials. Using first principles calculation, we can get physical properties at a given temperature and also thermodynamic quantity at a given temperature. And with this, not only toward this direction, but inverse design is also possible. So this is a current approach. Using first principles calculation, we can go toward both directions, which is quite useful. This is fast, skip, low labor intensive approaches. Oh yeah, I know that. And the broad first predictable power and inverse design possibilities. So the use of first principles calculation is twofold. One approach is principles-driven approach using fundamental laws and theories. Of course, this is very, very useful, and I really love this approach. But sometimes, or mostly, most of the cases, when underlying principles are not unknown or complicated, we have to use data-driven approach. So I will talk both of approaches, principle-driven and data-driven approach. One of the typical examples of principles-driven approach is to use the phonon calculation. Use a systematic set of first principles calculation and then put into the thermodynamic laws to obtain free energy at a given temperature, etc. So this is a typical flowchart for phonon calculation. And using force on each atom, for example, you can move atom from the equilibrium position, you can get forces, and solve the equation of motion to obtain phonon frequency as a function of the wave vector to obtain this kind of band structures. My colleague Atsushi Togo has been developing the code called PhonoPy, and this became a kind of de facto standard open source. And actually it was cited quite many times, and it's contributed to the community somehow. One of the typical examples, which I was very much convinced by the use of first principles calculation, was this figure. This is the case for zirconium oxide, which is a very popular subject for ceramics experimentalists. The Gibbs energy was computed as a function of temperature, and it is known that there is a phase transition with temperature from monoclinic to tetragonal. By experiment, it shows some kind of martensitic transformation. The middle temperature of this transformation was 1350. And the Gibbs energy showed intersection around 1350 Kelvin. So it can actually predict the phase transition temperature. So it was done some time ago, 20 years ago, but since then we have been working on phonon calculation. And also we investigated also the phonon-phonon scattering. Phonon-phonon scattering to compute lattice spurt of thermal conductivity. And this is quite straightforward, and this is the lattice thermal conductivity at 300 Kelvin experimental result versus DFT result. This diagonal line corresponds to the perfect agreement. Well, agreement is not so bad, and also from the experimental's viewpoint, Also, the experimental value are scattered somehow because some conductivity is very much dependent on the atomic defect. So it's very difficult to obtain high quality single crystal for these materials. So experimental value are somehow scattered. So we believe that this kind of comparison, at least calculational result, computed result is reliable, whose accuracy is at least comparable to experiments. So this is good news, but of course there is a bad news, the computational cost. This work was done 10 years ago, but still the situation is not very different. Since we have to handle so many phonon modes, and also for the phonon calculation, so the computational cost is 1 day work clock time per one crystal. So each of one crystal takes 1 day for the computation. So this is very lengthy calculation. And I will talk a remedy for this in a minute. A remedy is shown here. We have developed machine learning interatomic potential to solve this problem. Probably you know that machine learning interatomic potential is popular and many people are doing many different kind of interatomic potentials. And this is so popular subject. But what we are doing is a kind of very straightforward approach. Just to perform large set of first principles calculation and make machine learning potentials. And I will explain our machine learning potential in a minute, but okay, here. Our machine learning potential is shown here, polynomial machine learning potential. And this is basically expansion with spherical harmonics. This is not using the artificial neural network, artificial neural network, etc. This is just a straightforward expansion. The beauty of this type of expansion is you can control the accuracy-speed relationship. If you really need good accuracy, you have to expand up to a certain level. Then of course you have to sacrifice the speed to this level. By the way, this is for aluminum, and each of this black dot corresponds to one set of machine learning potential. So this is the highest accuracy, but this is something like root mean square error of 1 millielectron volt per atom. But if you do not need such accuracy, for example, if you want to handle much bigger system, finite temperature, then probably you do not need such accuracy, but 10 millielectron volt is sometimes sufficient. Then you can increase the speed by 100 times. So you can choose, depending on your purpose, within this Pareto optimal. But the good thing is, even if you use one of the most accurate potential, the speed is 10 to 5 times, 50 times faster than DFT calculation. This is 100,000 times, and it's a great advantage. For example, this is a result of the lattice thermal conductivity, as I have shown before. And this is the result for machine learning potential, and the vertical axis is by DFT. You can find that is an almost perfect agreement. So this identical result was obtained by 10 to 50 times shorter time. So 1 day computation time became 1 second. So it is a tremendous advantage of machine learning potentials. Okay, so this machine learning potential was developed by Seko, and he put in the GitHub, and for 48 elemental system and many other binary systems, this is expanding. And also he made a package for the interface for lamps, so you can immediately use for the molecular dynamic calculation. For example, as a metal resist, one of the familiar property for the computation is the grain boundary energy. For this type of simple grain boundary, you can do that by first principle calculation easily. But with the increase of the size of the supercell, DFT calculation became more and more difficult. But by using the machine learning potential, you can compute for the complicated system quite easily. This is the typical plot for the symmetric teeth boundary, grain boundary energy. And this violet one is for the machine learning potential. By DFT calculation, this is a cross point. This was obtained by DFT calculation, but this was possible only for the high symmetry boundary, but they are in good agreement. And for this type of calculation, there has been a lot of empirical type of potential available. And of course, the tendency is not very different, but quantitatively, they are not as good as the machine learning potentials. This is the same for many other systems, many other boundaries. This is for this element, the same for the other element as well. If you're interested in liquid metals, this is liquid silicon radial distribution and bond angle distribution. The left-hand side is the comparison between DFT and our potential result. They overlap perfectly, so you cannot distinguish these two. So above the melting temperature, the liquid metal structure, liquid silicon structure was very well reproduced. There has been a lot of other potential available, including Tarsov potential. Tarsov potential is very popular potential for silicon, but this has been tested only for solid. And it seems for liquid system, the result is not so good. Also for bond angle distribution. And this right-hand one corresponds to the crystal structure search for these binary crystals. And also for the metal resist, phase diagram is very important. And to construct phase diagram by first principles calculation, of course, you need the structure. And DFT calculation, you can calculate for many, many different kind of crystals and found these crystal structures are on the convex hull. This is the DFT result. The same thing can be done by machine learning potentials, and almost identical result was obtained. To construct this type of convex hull plot, you need quite good accuracy of the formation energy, but machine learning potential can be used for these purposes, which is a good information for the metal resist, computational metal resist. Okay, so the principle-driven approach is ideal, and we really love this approach. But unfortunately, the original material problems are unknown or very complicated. So principles-driven approach are not always useful. So we have to take data-driven approaches. Again, large set of material data by experiment and or by computations, and put it into machine learning and use for the material discovery. So where we can find material data, of course, NOMAD is a good source of the first principles calculation, and also for the experimental data, NOMAD. The database of crystal experimental result is shown by this type of databases, physical property as well. So they are source of the material data. By looking at, for example, ICSD result, this is a number of newly discovered compound within a pseudo-binary ionic compound versus year. So this green area corresponds to pseudo-binary oxide like this one, pseudo-binary oxide X is O. And this is all others. We can find that the number of newly discovered compound is somehow decreasing trend. It may mean that easily synthesizable compound and or compound in focused chemistry domain like lithium-containing oxide, iron-containing oxide, those are investigated by many researchers over years. They have already been discovered, so nothing left. It is a possibility. By the way, ICSD, up to the year 2000 or 2010, they basically piled up mostly experimental data. These days, they started to put many of the theoretical results, but this is a story for the experimental data. So there was a question, can we continue accelerate discovery of new compound? The answer can be obtained by looking at other type of historical diagram. This is quaternary or pseudo-ternary ionic compound of the same years. It seems this is still increasing trend. This suggests that there is a good chances for discovery of quaternary or more complicated system. But at the same time, for quaternary or more complicated system, there are millions or billions of combinations. So it is necessary to use an efficient method for discovery. Just doing trial and error to discover something in this quaternary or pseudo-ternary is very difficult, we can imagine. Okay, so this is starting on my major part of my talk. This is the motivation of the data-driven approach recommender system for discovery of CRC chemically relevant composition using ICSD database. So let me explain what is recommender system and what is CRC, chemically relevant composition. And there are two stories. The first one is using elemental features, and the second one is something different. Let me explain from this first one. This was also done by Seko and Hayashi, my group. So recommender system is what you can find on the internet, on e-commerce. Whenever you buy something, if you bought this book, the Amazon recommends you to something related to this item. This is sometimes called personalized advertisement. This is recommendation. So let me explain what is chemically relevant composition. If you look at this type of databases, you can find this type of compound in the database. They are existent. If you make a plot of free energy like this as a function of composition, this is convex hull, and these compositions are on the convex hull. So they are thermodynamically stable composition or crystals. And the others, they are not on the convex hull. So we can define that they are chemically relevant composition. By the way, I'm talking about some oxide which is equilibrium at thermal equilibrium and typically made at high temperature synthesis. So they are most cases in the thermal equilibrium conditions. So they are on the convex hull because of that. So they are CRCs, and the others are not CRC. Unfortunately, there is no general rules for what is CRC. So principle-driven approach cannot predict the presence of CRC. in some limited system, probably it is possible by looking at the structures. But in most of the cases, it is not possible. So we have to take data-driven approaches. So there are traditional approaches to discover new compound, like Linus Pauling did, based on the similarity concept. For example, the electronegativity or ionic radius, if this element A and element P has a similar ionic radius, they can assume that if this is existent, this may be existent based on similarity. And this type of similarity concept was somehow successful. And solid-state chemist has been working on this type of ways traditionally. We just follow this concept, but just expanding the dimensions. This is a two-dimensional plot of feature 1, feature 2 for the crystal structures, crystal compositions. The ICSD registered compound are plotted like that. And these are grid point. And most of grid point, it does not correspond to the ICSD registered compound. We simply use the feature space to be something like 500 dimensions. Here, only two-dimensional. So ionic radius, electronegativity, but we use 500. But the method is the same. For this grid point, this can be non-CRC, or just simply unexperimented, or just simply difficult to be formed. But anyway, we want to distinguish ICSD registered CRC or non-CRC. So what we used was a very primitive binary classification approach. So this is from the scikit-learn textbook. And if you have this red point and blue point, you can use many different kind of classifiers. And if the result is based on a validation, if the result is good, then the classifier is considered to be good. So we have tested many different kind of classifiers and found that these three works quite nicely. And for the chemistry space of search, we use for the learning data to be 33,000 of ICSD registered training set, and to discover something within 1.8 million of ICSD unregistered compositions. And for the elemental features, you can find so many numbers on the periodic table. There are sometimes some atomic numbers, atomic mass, or electronegativity, or ionization energy, or sometimes boiling point of element or density, whatever. But there are only 22 something. So we use all of them. On top of that, for compound AB or this compound, we put all these elements in a feature space and gave the weight for this number. For element E, it's 4 times more weight. And get the average variance skewness and also covariance. By including covariance, we can increase the number of features. So it becomes something like 500. So using those 500 features and binary classification, this figure shows the number of compounds included in ICDD versus the ranking of the predicted probability or the recommendation scores. We use ICSD data as a training set. And ICDD, this is another database, is often used for the X-ray powder diffraction. There are a lot of overlap between ICSD and ICDD. We use only this yellow part for the training and the less of data for the validation or test. So the vertical axis corresponds to the success rate of this recommendation. From the top ranking down to 20,000 ranked one, the number of correct answers somehow decreased. This gradient corresponds to the efficiency or the success rate. And this bird chart corresponds to the gradient of this plot. This is a cumulative plot. Here is 1,000 highly ranked composition, and among 1,000 top-ranked compound, 180s are found in ICSD database. It means a success rate of 18%, which is 60 times higher than the random search. Random search can find out only 0.29%. So this is 60 times higher. We can plot this type of recommendation score plot. And sometimes you can see some red dot which correspond to the higher probability of the existence. By the way, this is pseudo-ternary plot. And here the element and member is changing. Sometimes this is also changing. So by showing this type of plot, experimenters are excited and they try to synthesize new materials. For example, this is professional people for the ionic lithium-ion battery, and they are searching some oxide which shows good ionic lithium-ion conductivity. And according to our recommendation score, they have searched these 6 composition, and actually they found this new compound based on the experiment. And also for this pseudo-ternary, they found this this composition. So they were very happy to find this type of new compound because they know how to modify these new crystals by doping and so on. And also for nitride, for this pseudo-ternary nitrides, there were a lot of candidates. And from them, those professional synthesized people found this new nitride material, and they succeeded to analyze the structures. So it seems the elemental features based recommendation score works quite nicely, but we are not very much satisfied by that result because the success rate was only 16% for top 1,000 ranked crystals. So we try to improve our recommendation system with the help of the information scientist. What we use is a tensor decomposition technique. Here again showing the recommender system with from Amazon.com or e-commerce. They typically has a really long list of users, sometimes billions of users, and they know who bought which items. Based on this data, they gave a recommendation score for the target users. If this target user is interested in buying this item, if the recommendation score is high, then they put in a personalized advertisement. The algorithm for this recommendation system is very simple. This is so-called rating matrix, the huge customers list and the items what they bought. And there is an underlying assumption that people with similar taste tend to buy similar materials. This is from the physics viewpoint, it is not supported, cannot be supported. But from the social behaviors viewpoint, this is very understandable. In mathematical language, this is called a low-rank structure of this rating matrix. Based on this unsupported assumption, but reasonable assumption, we just rearrange this matrix element to make this type of plot. Then, based on this rearrangement, we can realize that customer A, C, H behave similarly. So maybe customer A and C is interested in buying this element, this item 3, and also for the other customers. So we try to apply this method to discover new CRCs. So here we expanded our chemistry space up to quinolate system composed of 66 cations and 10 anions. And the composition ABCDX is up to 20. So it becomes 23 billions of candidates. So it's a lot. But our training data set is not easy to be increased. So the training data set contains only less than 10,000 compositions. If you compare it with the number of candidates, it's a huge difference. But we have to use this one. There's no alternative way. So we use this ICSD data again for the training, and this pink area for the test, for validation. For the rating matrix, instead of using matrix, we use tensors. This is for the binary system, cation type 66, anion type 10, and the integer set for the composition. So for the binary, it is only 100,000 of compositions, but for ternary, quaternary, it becomes fourth order, fifth order tensors, but it can be handled quite easily by using the software like in scikit-tensor. We have tested many decompositions algorithm and found that Taka decomposition worked quite nicely. Basically, the big tensor is decomposed into small tensor with here 3 matrix. This is already a result for the recommender system. The horizontal axis corresponds to the length of the small tensor, and the vertical axis corresponds to the number of correct answers or success rate. The orange shows the top 100 compositions, almost independent of the length of this small matrix. The result is quite good. Here is 100 composition. Here you can see about 59% of the candidates are included in ICDD or Springer materials. It means discovery rate is something like 59%. This is really surprising because we didn't use any prior knowledge, no elemental features, no first principles calculation, nothing. Even if we do not use such a prior knowledge, just by simple rearrangement of tensor element, we were able to predict such a high probability new CRC. It's the same for top 3,000 compositions with high predicted rating. Discovery rate is 25%. Using elemental features, it was only 15% for top 3,000. So this is much better than using the elemental features for binary classification. Of course, we want to validate using different methods. The easy way for us is to do first principles calculation, a set of first principles calculation. And for the rubidium-indium pseudo-binary, we found two compositions shows quite high recommender scores. So we built up formation energy convex Hall by first principles calculation, and actually they are on the convex Hall. So by the first principles calculation, these two compositions are confirmed to be thermodynamically stable. It's the same for 27 different systems. Something like 85% are confirmed to be thermodynamically stable by DFT. So we're satisfied, but at the same time, we put in an open database and let experimenters work on that. Of course, we want to work, since I have been working in experimental field, so I want to synthesize new material by ourselves. But the synthesis recipe of new or as yet unknown compound is not that easy. Because since this is new material, it is not shown in a cooking step-by-step book. So we have to consult synthesis expert how to make it, or use of artificial intelligence. Even if we ask synthesis expert, they are based on their empirical knowledge from the database somewhere, and they use their human intelligence to say something about synthesis condition. So we saw that artificial intelligence can work better than a synthesis expert. That is the motivation of my last part of my talk. This is a data-driven approach to find out synthesis condition recommender system based on parallel experimental data set. This was also done by those people, basically. So our experimental capability is quite limited, but we are able to make this type of synthesis system using this type of very primitive robots and using polymerized complex methods. So basically, these liquids are mixed together by this robot and dried and fired and automated powder X-ray diffraction to identify the crystals. For the starting materials, we have chosen these cations, 28 elements, and the 32 starting materials for the polymerized complex method. And we investigated only pseudo-binary oxide because our lab is not very much specialized. We do not have special environment for nitride or non-oxide system. Oxide is much easy to be synthesized by the people like us. But at the same time, pseudo-binary oxide, there's been a really long history, much more than 100 years, to synthesize pseudo-binary oxide. So many people came to me and say that, Isao, you said you're going to work on pseudo-binary oxide, but since pseudo-binary oxide has been investigated more than a century, so there's nothing left over. So it's better to stop that. But I didn't follow that suggestion, and we tried to find out something new in pseudo-binary oxide. Actually, there are 28 elements with 27 elements. So altogether, the candidate composition is something like 10,000. And this is the chemistry space of 10,000. And within this 10,000, about 10% this red zone is known composition for the existence of crystals. And 90% are unknowns. And many people suggested that there is nothing left over there. We tried to synthesize with 66,000 different synthesis conditions. Among these 66 synthesis conditions, we made some synthesis experiment for these cases, randomly chosen from this zone which correspond to the known composition and the others which correspond to unknown compositions. Even within known compositions, only 50% of them are succeeded to synthesize crystals of the targeted composition. 50% are not succeeded because although they are known, but some of them requires special technique to synthesize, like high pressure synthesis or special starting powder to be synthesized. So this is quite reasonable. And also for this green zone, 100% are failure. It suggests that it is difficult to synthesize new compound in this zone, 100% failure. But anyway, we use these altogether 1,500 conditions used as a training data and put all data into the recommender system. So synthesis results are scored according to the powder X-ray diffraction. If it is synthesized successfully, then we give a score +1. If it is not successful, -1. And put all these data into the tensor. This is fourth order tensor with starting material number 1, number 2, composition and firing temperature. And this orange one is successful, blue one is unsuccessful, and white one is unexperimented in the original tensor. And after the Taka decomposition, we can estimate the recommendation score for the unexperimented condition. And for the unexperimented conditions, we did synthesis experiment again and found if it is successful or not. And this figure shows fraction of successful condition versus predicted score or recommendation score. This is almost proportional to the recommendation score. So success rate is almost proportional to the recommendation score we found. So we ranked all the recommendation score from the top down to the bottom. And within top 300 recommendation scores, we found here 75 compositions with 135 synthesis conditions. And we tried everything and found out this lanthanum vanadium crystal, which is existent and newly found by this experiment. Another one is lanthanum antimony oxide, which shows these structures and discovered by this experiment. So people said it's nothing left in this green zone, but actually by using efficient method we have developed, it was possible to discover these two compounds at least. Since our training set is quite limited, if we increase the number of training data, of course we will be able to discover much more. But if we increase the number of training set, then it is no meaning to use this type of recommendation system. So there is a balance of increasing training set and the area for the candidate space. But anyway, this works quite nicely. So using parallel experiment and using recommendation system, we were able to discover something. And based on this result, we are going toward the direction for the autonomous experimentation. And this is not yet done or still in progress. And this autonomous experimentation is a kind of hot topics in the world, but we are not doing so nicely. But using our experience and also DFT calculation capability and this recommendation score, in the future, we will be able to do some autonomous experiment for the targeted examination. So this is the end of my talk. Thank you for attention.